we can start. So next speaker is Sergei Fedotov, and title is on display, and understanding is that you're going to relate this to biofilms.
Right. First of all, thank you very much for inviting me to give a talk, Luca. Special thanks. And so today I'm going to talk about reaction subdiffusion equations. So from a mathematical point of view, it means nonlinear in time fractional PDEs. So my main purpose today is to show how to derive this equation, how to develop this equation from underlying random walk. And a very specific feature of this equation is that there is no unique reaction subdiffusion equations. These are very sensitive to underlying random walk. So I create a variety of different equations. For that reason, it's very important to take into account all these details of random walk on microscopic level, because those equations on microscopic level got quite different properties. So simple phenomenological approach as a reaction diffusion equation doesn't work. You can't formulate reaction subdiffusion equation from phenomenological picture. And the reason why we're interested in reaction subdiffusion equation is a particular problem of penetration of antibiotics into biofilms. So this is work in progress, and I will give you some preliminary result. So, but first let me give a brief outline of my talk. At the beginning, I will discuss and remind you about subdiffusive transport reactions, and as illustration, I will use heterogeneous biofilms. So not just in an abstract level, but using biofilms. Then, because biofilms is very heterogeneous, so it's very important to take into account the dependence of anomalous exponents on the depth, on the space. For that reason, I review in the second part space-dependent variable order time fractional diffusion equation. So my main part in the part 3, I will show you how to implement reactions, including nonlinear reaction, into subdiffusive transport by using standard model continuous time random walk. And the last part, it's about superdiffusive transport in C. elegans, and also I'll take opportunity to discuss, actually I will share my experience working with biologists, because a lot of work's done here on subdiffusive, superdiffusive transport together with biologists, and this very interesting experience. So that's my plan. Right, so first look at this picture. So this is a part of biofilm, and biofilm of course contains bacteria, but also bacteria wrapped on a very special substance, so-called extracellular polymeric substance. And this substance, of course, forms the structure of biofilms, and at the same time, it acts as a barrier, physical, chemical barrier for penetration of antibiotics. So if you look at this color, the yellow one, this represents antibiotics, and you can see that antibiotics are concentrated, aggregated on the periphery of biofilms. There is no penetration. So, but the purpose is, of course, to kill bacteria here. But in deeper layer, they survive. So this is a very huge problem, and it's called drug resistance infections. I'm sure you heard about this. And okay, I'll give you just one scary slide. So just to illustrate the importance of the problem. Again, slow penetration of antibiotics. So in this country, the UK minister, health minister, reported recently that 8,000 people died every year in this country because of that drug-resistant infections. So, and you can see, this is again antibiotics, and they just can't penetrate here. Why? Again, because of this substance. And we hope that by using reaction subdiffusion equations, we could contribute a little to solving that particular problem. Because nowadays, and that's what I'm going to discuss, the reason why the antibiotics or nanoparticles trapped here on the upper layer of biofilms is due to subdiffusion. Okay, so that's our hypothesis. Right. Now, if you look up, then you see the standard PD. So, of course, for many decades, that problems of penetration of antibiotics tackled by kind of reaction diffusion equations, standard PD. This is, of course, standard one. On the right-hand side, you can see diffusion. Diffusion usually depends on depth, of course, because it's highly heterogeneous. Because here, it's a very complicated ecological system. The bacteria exist in a different phenotypes. And so I'm not going to discuss this complexity of biofilms. For me, it's important just penetration of antibiotics or nanoparticles. So that equation, and of course, it's very easy to solve it and under appropriate boundary conditions and get the profile of antibiotics. But the problem is that recent evidence show that there is no diffusion. It's subdiffusion. We need to use proper equations. But as I said at the very beginning, you can't write down subdiffusion reaction equation like this one. That's very easy to write down. Transport, reaction, how extent easy. You can use, for example, other equations for concentration of oxygen. It's very important. You can write down equations for bacteria in different phenotypes. And all the time, up to now, apart from one or two works, it's always reaction diffusion equation. Why? Of course, because numerical methods for PD is well developed. So it's a very nice tool. But as I said, there's a new evidence that it's an anomalous transport behind this slow penetration. So, now the question is how to take into account subdiffusion. First, let me show how it shouldn't be done. So, typical situation is the following. Let's say rho is a function of time and space. This is concentration of antibiotics. We write down equations. So the rate of change. And let me write down in a simple form. Diffusion, second derivative with respect to x squared, minus degradation term. So this is a standard way to deal with the problem. Now, how to take into account subdiffusion? At first glance, you can do it something like that. I just put here mu. Call it Caputo derivative. So I've got subdiffusive reaction diffusion equation and solve the problem. This approach is completely wrong. So you can't simply substitute standard derivative on the left-hand side by fractional derivative. But nowadays in physics or in chemistry, it's like epidemics. So people take derivatives, basic equations in chemistry, physics, change standard derivative to fractional derivative without any discussion of underlying physics, chemistry, and so on. It's just really epidemics in fractional business. So sometimes you can justify it, and that's okay, but sometimes it's just wrong answer. So this approach is really wrong, and I will show you why it's wrong, of course, with all details. Okay, so, right. So this is just an example of recent papers. So if you read the title, it's anomalous diffusion of nanoparticles in this partially heterogeneous biofield environment. So this is just another example. If you ask me why nanoparticles, because in order to penetrate deeply into the layer of biofilms, nowadays people started to design nanoparticles, so-called neutral nanoparticles. Why subdiffusion? Because I'll give you an example. Antibiotics might be positively charged particle. And then it penetrates, then this substance in biofilms involves a lot of DNA, which is negatively charged. So we have charge-induced trapping. So, and trapping might be very long. So people usually say, okay, this is so-called reversible absorption. And that absorption had a long tail, and it might be like first moment divergent, and that's why we have subdiffusion. So, and now they say, okay, now we could design new particles, neutral. They penetrate deeply. But again, there is evidence, it's just anomalous diffusion for different reasons, so subdiffusion. And I am aware only one paper, and another one is very simple, Kostolovich and Messler, who deal with subdiffusion reaction to this particular problem. But they use a lot of simplifying assumptions. For example, like anomalous exponent is constant, which is really not good for biofilms. That's what I'm going to explain in a minute. All right. Okay, this is just, of course, a reminder. What is subdiffusion? When we have mean square displacement, it's not linear function of time. The reason why I remind you this, because if you look at this parameter mu varies from 0 to 1. So for the rest of this lecture, I'm going to use as an anomalous exponent notation mu. So please remember, mu is anomalous exponent, varies from 0 to 1. This is extremely important parameter for us. Okay, so that's a reminder. And now let us discuss general stuff. So before I'll turn to biofilms, let me discuss a general idea behind reaction subdiffusion equations. So let's, the density represent just abstract particles. And the standard advection diffusion equation, of course, is almost trivial. So you can see that the change of the concentration on density depends on two terms. We have advection with incompressible fluid flow diffusion. And if we want to take into account reactions, any reactions, what we do? We simply just add on the right-hand side term, and we call it that's reaction. It might be positive, it might be negative, it doesn't matter. The crucial things, so that's very important for reaction subdiffusion. You see, advection, diffusion, reaction, they're all independent. So, of course, it's easy to extend phenomenologically. You can write down 3, 4 equations, add different kinetics. That's very easy. It does not work for reaction subdiffusion. That's a message. So, if we write down equation like this, for example, time fractional PDE, of course, in physics we call it Fokker-Planck equation, fractional Fokker-Planck equation. It involves fractional derivative, Riemann-Liouville. Of course, again, we have drift, we have diffusion, but now if we just treat the density of particles, we can't simply add non-linear terms on the right-hand side. We can't do that. Of course, I will explain in a minute why we can't do that. So, so by the way, this definition of Riemann-Liouville derivative. So it's a rhetoric question. This is a good model for reaction transfer. The answer is not. In some particular cases, and that's what I'm going to discuss, it works, but a very particular case. Most of the time, it doesn't work. So it's clear message that it's very difficult to extend standard diffusion model, passive anomalous diffusion model, to the reaction subdiffusion model. And now I'm going to give you a few examples how to implement reactions into subdiffusive transfer. Okay. Again, we have a very simple model. Now it's a linear kinetics. So this is a constant degradation rate. We have a diffusion. Now, how to extend this equation when underlying random process is subdiffusion? Because, of course, behind this term, second derivative of Laplace, we know it's Brownian motion. Okay? Now, what is underlying physics and what is underlying process when we have subdiffusion. Right. So this is right time fractional reaction subdiffusion equations. These equations was derived a while ago. It's in 2006 by Bruce Henry and his co-authors, and also Igor Sokolov is his course. It's a long time ago, but this is right equation. Look at the structure of this equation. It's very instructive. Of course, we have the same degradation term on the right-hand side. But now look, this is transport operator. And this transport operator involves degradation rate. So it means you can't separate transport and reaction anymore. So reaction got a huge impact on transport operator. Look at this. Of course, this is just a second derivative with respect to space. But now you see this is extra term, exponential factor. And of course, this is a standard Riemann-Liouville derivative. So even in now you can see this doesn't work. So that's obvious. And this term, this factor, plays a very important role. I will try to explain physics. Because, of course, I'm going to derive this equation. Just give you a general idea how to derive that equation. But the following idea, let me explain the main idea. You see, this is exponential factor. And in order to kill subdiffusion in a standard models, we introduce tempering. So if you have a power law distribution for waiting time, and the first moment is divergent, we have subdiffusion. Okay? Now, of course, subdiffusion in long time should be a standard diffusion. How to do it? You have to cut power law distribution. Usually it's done by multiplying by exponential factor, and you say, oh, that's tempering. So intermediate behavior subdiffusion, in long time, it's standard diffusion. But here, that's tempering occurs quite naturally. Because when the particle is trapped, is from probabilistic point of view, two ways to proceed further. Either to die or be trapped. And in long time, if you've got a killing process, that killing process just kill long waiting time distribution. So it's quite natural. It's not just artificial regularization. So, and then, for that reason, despite the fact it looks very complicated, in long time, it becomes like diffusion-like process, but diffusion coefficient becomes dependent on rate. And that's the consequences. So regularization leads to the standard diffusion at the end, but diffusion coefficients depends on degradation rate. That's an interesting interconnection between kinetics and, of course, subdiffusive transport. Okay, I will show you how that can be extended idea for even for nonlinear case later on. So first work started in 2006. And since then, it's a lot of work done in this area. And right. Now, why this exponential factor with reaction or degradation rate appears in transport operator? That's what I need to explain, I guess, and that's what I'm going to do. Right. So usually, when you deal with a non-Markovian random process, in particular continuous time random walk, when waiting time is not exponentially distributed, you formulate a so-called renewal equation. It's very difficult, believe me, to implement reaction, especially non-linear reaction, into renewal equation because they are written in integral form. Of course, these people are clever enough, they managed to implement it. But calculation is very complicated. And we know from probability theory that if you have a, let's say, non-Markov process, better to say semi-Markov in case of continuous time around the walk, you can extend phase space and make the process Markov. And as long as you do this trick and you have deal with Markovian equations, it's very easy to implement anything. So for that particular case, instead of density, you can introduce structural density. So let me explain. So this is function of time, x, and then you introduce extra variable, tau. Tau is a variable which describes the following situation. So this is the density of particle at the time t, at the point x. I'm talking now about continuous time around the walk, with aging or waiting time in this interval, okay? So we structured the density, okay? Now, equation for this function can be written very easily. Of course, it's the rate of change. Also, of course, we have advection in terms of tau. And then here we have to put gamma. If gamma is constant, it corresponds to Poisson random process. But in order to get subdiffusive behavior, we have to assume that gamma is dependent on waiting time. Okay. Usually, when you deal with continuous time random walk, you always start with distribution of waiting time. So, just power law distribution, you formulate the renewal equation and do the whole analysis. But in this approach, you introduce the rate, which depends on waiting time. And if you assume that this rating proportional to mu over tau, which means the longer you stay in the trap, less likely you escape from that, you will get subdiffusive equation. Why I'm talking about this? For two reasons. First of all, it's very easy to extend this equation for reaction. Now you can put reaction in this equation, and that's quite legitimate. And another reason is that because I told you at the very beginning, I would like to share my experience working with biologists. Subdiffusion, as you might remember, occurs as a result of divergence of first moment. So you've got power law waiting time distribution, heavy tail, and first moment is divergent. If you tell biologists that first moment is divergent, that's why we have subdiffusion, it doesn't work. And if you say, oh, the mean time is infinite, it sounds like rubbish for biologists. So how to persuade? Biologists observe subdiffusion all the time. So that's my experience. They know what is subdiffusion. It's just the growth of second moment, non-linear, subdiffusively. So, but how to explain? If biologists ask you, oh, what is the reason of subdiffusion? How to explain? Heavy tails distribution? No, it doesn't work. But if you say something like that, in terms of rate, you say, okay, particle trap, the longer particles stay in this trap, less likely it escape. And just miracle, it works. So, because it's just an idea, it's the same for superdiffusive transport. We know if we have superdiffusion, let me remind you, like Levy walk, it should be second moment of running time should be divergent. If you say this to biologists observing superdiffusion, oh, second moment is divergent, it works for biophysicists. That's okay. It works for us, but not for biologists. So you always need to find the proper language. That's what I'm saying. So in terms of kinetics, it's easy to find. So always I explain things in terms of Markovian models. Now, what is the relation between rho and psi? Of course, the rho can be obtained just simply integration or eliminating this variable tau. And since you had that equation, you can solve it because it's a linear equation. It's easy to solve. And you can define so-called escape rate, so-called anomalous escape rate from the position x at the time t. So how to do it? It's here. So you have to integrate this term again from 0 to t. So rate psi d tau. Now, also you need to formulate initial conditions in terms of tau, sorry, boundary conditions. So, and this is rate of arrival. So the value of psi at the point x at t at the time 0. So if you consider the space, this is x, particle of course escape from that position, but they're coming from different position from here, and of course when they arrived at this position, the waiting time is 0. So that's how we formulate that. So you just need to double integral from 0 to t over all space, because the particle coming from different position, and you just integrate this rate tau, and of course you have to evaluate psi at different position, x minus z, t tau, and you introduce jump distribution. So the rate of change of the density of particles at this position, of course, it's escape rate plus arrival rate. So this is master equation. And now I give you these details just to explain why we have these funny equations. Now follow me. In order to get arrival rate or escape rate, you have to solve for psi. And psi looks like this. And it involves healing rate. So inside this term will be parameter A, inevitably. And then if you use diffusion approximation, you will get that equation. So that's the main idea. If underlying random process is Poisson, so it means that escape rate from x and t will be simply Poisson rate and the density. And that's Markovian model, this independence of reaction and transport. But in that particular case, you don't have this luxury, and this escape rate from this position depends on, of course, underlying random walk and what happened in prehistory. So, of course, I could explain this in a few words, because it's not innocent operator. It's integral over time. So it takes into account whole prehistory. And of course, reaction influence the distribution of particles in the previous time. So inevitably, the transport operator involves reaction. Okay, so this problem can be, of course, extended. This is just also done almost 15 years ago. If you introduce degradation rate as a nonlinear function and you split on plus and minus, then you will end up with a very complicated equation like this one on the top. But interesting feature, so if you look at that equation, I'm not going to describe the detail, But you can see that in transport operator, it appears only R minus, not R plus. Okay, wait. And the reason is the following. Look at this condition. So this is a boundary condition for particle arriving at particular position. So if I add here extra term R plus psi, it means newborn particle have 0 waiting time. And then this term appears only here. That's why it's just extra term, like plus, and here I put R rho. So the conclusion is very simple. If you have a new particle due to birth process, and if you say, okay, the aging is 0, or waiting time is 0, you've got additive process. But if you say the parents, let's say, of new particles got particular time, and if you say, okay, waiting time is just the same as parents, then the reaction rate appears in the transport operator. So that's what I said at the very beginning. There is no single equation for reaction subdiffusion. Everything depends on these details. How you organize waiting time distribution corresponding to kinetics. And of course, the final decision whether it's right or not, it's just experiments. So I could create a variety of reaction subdiffusion equation. So this is just one of them. So again, you've got birth, you've got death, and you see, again, we have nonlinear exponential factor inside transport operator. Now back to heterogeneity. Well, again, the main challenge, as I said, implementing reaction terms, but extra problem here, it's a depth-dependent anomalous exponent. So far, all this work I mentioned already done for the case where anomalous exponent is a constant. But if it's not, it creates additional problems. Actually, a lot of problems. Let me explain why. Okay, so now here is a two-time fractional Fokker-Planck equation. One Fokker-Planck equation written in terms of Caputo derivative. So of course it's just drift. You've got diffusion, and you see the diffusion coefficients depends on space. Drift also depends on space. This is another formulation of the same time fractional Fokker-Planck equations. Now it's written in terms of Riemann-Liouville derivative. It appears here. So both descriptions are equivalent. That's what we know. If you perform, let's say, Laplace transform, you will get the same equation. Now my question is, why here? So fractional Fokker-Planck equation involves 3 parameters: drift, diffusion, and anomalous exponent. Why 2 parameters? Depends on x, and anomalous exponent doesn't depend on x. We know the answer. Why is that? That's very typical. If you look at equations in that business in the papers, most of the time, diffusion depends on x, drift, but anomalous exponent is always constant. Why is that? Of course, because it's easy to deal with. That's obvious. Look at this equation. Mathematicians like this writing because if you say to mathematicians what is subdiffusion, the most likely answer will be, oh, this is just time change. They've got inverse stable subordinator. You've got standard operator underlying random walk. But if you have, let's say, long time trapping, then you introduce extra time, and then it leads to this equation in terms of Caputo derivative. In physics literature, people prefer Riemann-Liouville derivative written in this form, because that equation can be derived, let's say, from continuous time around the world model. Very easy. So here, we just through the subordination in terms of inverse stable subordinator. But mu is not constant in many cases. Now, of course, the clever people in the past who decided to say, well, anomalous exponent is not constant, because anomalous exponents actually physically describe the strength of trapping. Why trapping here is different from here? Of course, in general, they are different. So anomalous exponent should be function of x. Now the question is how to take into account. And again, you need to look from first principle, from continuous time random walk. And these three guys, 2005, first time derived variable order fractional PDE. So now you can see that anomalous exponent appears in this bracket. So you take a second derivative with respect to x, and mu appears here. So you can't rewrite this equation in terms of Caputo derivative anymore. You see? If someone say, okay, we have Caputo derivative, and then say, now mu is not constant, but a function of x. This is very artificial. No underlying physics behind. So you can't just manipulate with formulas when you deal with fractional equations. You always need to be based on underlying physics. So, and this equation has so many different properties. So I mentioned just three papers, one mathematical, these two, in which is many very specific behavior. For example, there is no Boltzmann distribution at the end. For that particular case, there is no uniform distribution under appropriate conditions, because this dependence of anomalous exponent depending on x generate very funny, and that's, oh, by the way, just also I want to mention, also it depends on the way you treat the model, either local model or barrier model. And equations are completely different. So this is just two equations. You see, this is second derivative, you've got this product. But also for barrier model, you see the derivative and this written in a standard form as a flux. So, and this small difference in analyzing microscopic behavior leads to quite different macroscopic equation. So, because there's no time, I skip. So, for example, if you use local model, anomalous exponent generate the flux. You see, this is a standard flux corresponding to the gradient, but this flux also involves this very complicated operator proportional to the derivative of anomalous exponent with respect to x. And this fractional operator looks like this. So you see, you've got extra factor compared to Riemann-Liouville derivative. Again, this term disappears for barrier model. Which is the model is right? We don't know. So it's very sensitive to underlying microscopic picture, what is going on. So in terms of aging, in terms of specifying, so if you start from master equation like this, so where to evaluate anomalous exponent, locally or in the barrier? Of course, when you put A tends to 0, you might say, oh, there's no difference. A is the size of the lattice. So if A tends to 0, you've got diffusion approximation, but it's very sensitive. Of course, it's got similarity to this problem of Ita Stratanovich. But Inter-Stratanovich problem is solved. As long as you've got color noise, the asymptotics tends to Stratanovich interpretation. But here, it's not clear what is the right model. So 5 minutes left?
Yes.
So, now we have equation for biofilms. Again, this equation involving derivative. This is, of course, because of porous media. You've got nonlinear degradation rate. What about operator for this problem? Operator is quite complicated. So this is transport operator. And at the very beginning, I told you, we have here regularization. So at the end, if you want to calculate the profile of antibiotics, you can get it from that simple equation. So in long time, this is complicated reaction subdiffusion equations tends to the standard equation, but then diffusion coefficients now becomes on non-linear degradation rate. Of course, when mu is 1, we have standard subdiffusion. This term disappears, and then we have a standard expression for diffusion. So this is the size, a squared over tau. But in general, it depends on, and this is only for local model. For barrier model, equation, subdiffusion reaction is not available. So I've got only 4 minutes for discussion, so I will end. Thank you very much.
So, thank you very much, Sergei. So, yes, some time for questions.
What are initial conditions for rho if t is 0?
Ah, right. It's a very good question because I start from 0. So I assume all particles got a 0 waiting time at the beginning.
Is it possible to formulate this equation for non-zero? For assume that you have some history.
Yeah, if you have some history, oh yeah, this is a very good question because usually people write down the fractional equations. They don't care about initial conditions. But if you care about initial conditions, what happened before, you've got extra term, and it's ugly terms.
And what about uniqueness
Oh,
of a solution?
I didn't analyze that, to be honest. You see, like for barrier model, the equation is not available yet. So, but in the long time limit, I will get a very nice equation because of tempering. But no,
because
that's I analyze
when you want
mathematical
to solve equation, you have to use some numerical methods. And if you wish to get the true answer, you have to have uniqueness of a solution.
No, that's what I said. We did not do that yet. And probably we're not going to do that, to be honest. Of course, Monte Carlo simulation is the best method to solve that equation. Because we know underlying random process. Because finite difference scheme is nightmare for this kind of equations.
Talking about initial conditions, probably you have also aging properties there that you could take into
Yes,
account.
yeah, of course. This is, yeah, that's what we assume. Because for, let's say, biofilms, you put all particles on the top, and of course, initial conditions organized that way. So waiting time for them is just 0 initially. So it's quite natural.
And is it possible to formulate an equation not for rho, but something like psi, when the aging is included?
Yes, of course. No, that's what I said. You've got additional term, integral from minus infinity up to 0.
So maybe you don't have to write the equation for rho, but for psi, and study equation.
Yes, that's what we did. We published that paper together with Peter Strache. So we got this term, but then we gave up because if you want to reduce to rho, then it's a nightmare. But yeah, this, of course, if you have a memory, you have to take into account what happened up to time 0. Technically, it will be just very specific integral from -infinity to 0.
I mean, for psi, maybe you have existence uniqueness even if you have second derivative.
Yeah, you are right, because it's a Markovian model. Yeah, you can deal with that. Yeah.
But Markovian, but with certain bad term tau.
Yes, it's.
Okay, any further questions for anyone? I want to have some coffee. Okay, let's thank the speaker again.
Thank you very much.